In today's video, we will produce 1 kilogram of potassium metal in just one distillation. But wait. What exactly is potassium? Potassium is an alkali metal, one of the very soft and reactive metals located on the far left of the periodic table. You can easily cut it with a knife and deform it with your bare hands. And when it comes into contact with water, this happens. However, potassium is quite expensive.
This is not okay.
I don't think that picture is correct. Anyway, wouldn't it be great to produce potassium in large quantities from raw materials that you can buy dirt cheap in 25 kilogram bags or as waste? Over the past few months, Elias and I have been working on a method to produce potassium metal on a large scale from inexpensive reagents. For this, we used my small stainless steel still, which I have also used to produce cesium and rubidium. And once we found a suitable method, we decided to scale it up. So I designed a huge 10-liter still in CAD, and a channel viewer, Fabian, helped us adapt the pipes on his large lathe.
Einmal drauf ist an, nochmal drauf ist wieder aus, oder was?
Als hätte das ein Profi geschweißt.
And with my total of 5 hours of welding experience, I can now say without a doubt that TIG welding is superior to all other welding methods.
So I would say we take all of this to Elias and see if we can make potassium on a kilogram scale.
The potassium is produced in a reaction between potassium carbonate and magnesium. We mixed magnesium shavings, which we've purchased cheaply as waste from milling or turning operations, with potassium carbonate, which has been dried for 2 hours in an oven at 250 degrees Celsius. In the actual reaction, the potassium carbonate is reduced by the magnesium, resulting in elemental potassium, magnesium oxide, and carbon being formed. After this reaction, we can distill off the potassium. The starting materials were well mixed and then filled into the still.
Now that we have filled the reaction mixture in our still, we are going to light it on fire, then close off the still and distill off the potassium that has been produced. And we will also put this steel can on top of the CF flange to prevent the potassium from just evaporating. Since it's the first time we're doing this reaction, 30 times the scale we did before, we went outside and far away from anything that could burn. It's very wet, it has rained a few minutes ago. And to light the reaction mixture on fire, we will be using
unicorn tears
and glycerin, because I think it's the safest way to have a time fuse, so to speak. Oh yeah, you can see the potassium condensing, yeah.
Guys, you do realize you're transferring oxygen from one metal to another, right? That's basically a thermite reaction. You should not be so close to it. Yeah, that would happen. At least you guys still have your eyebrows.
What you just saw was incredibly reckless on our part. One should never underestimate a reaction and approach it without extensive experience and the ability to assess how it will behave. It is important for me to emphasize that this situation could have easily gone wrong and definitely did not set a good example.
I think we've lost some potassium here.
Poking around in there with a stick is also a good way of making this blow up on you. Please don't poke in there with a stick.
Safe. Super!
The still was then placed into a propane furnace. An electrical furnace would have been a lot better to precisely control the temperature, but we don't have one. As you can see, we are using a CF flange with a copper seal to guarantee a vacuum-tight seal, even at high temperatures. A 2-liter round bottom flask was attached using a homemade KF25 to NS29 adapter.
Genau so mit dem so drücken, das würde ich nämlich nicht machen. So ist es doch kaputt gegangen.
Die gemacht, ich weiß genau, was die aushalten. So.
Oh!
After we noticed that no more potassium was dripping into the receiving flask, we turned off the furnace, waited for the still to cool down a bit and introduced argon as a shielding gas so we could take off the round bottom flask without oxygen getting into it.
Some slight overpressure.
To determine the yield, we melted the potassium under a layer of mineral oil and poured it into a beaker. After it solidified again, we weighed it. The yield was 320 grams, which corresponds to approximately 24%. Considering that a large amount of the reaction mixture was expelled from the still, not bad, but still far from our goal. Subsequently, it was time to open and quench the still. No matter how efficient the distillation is, there will always be highly reactive potassium residues in the still.
Who wants to quench this?
Das kennst du mit dem Gartenschlauch, der ist, also...
Junge, Junge, mach mal langsam. Oh, oh. Der Old Chemist, der Bold Chemist. Der Old and Bold Chemist.
Okay, it is now 1 week later and today we will try again, since the reaction last time was a little bit too violent for our liking. Fabian designed a very special piece of equipment, this thing right here. On the one hand, it has this flange here, which protects our CF flange on the still, and via this deflection shield right here, if anything out the still is thrown upwards, it is directed to the side, so it won't fly up into the air. And we also decided that we won't do a huge batch again like the last time, so we're not letting 4 kilograms react at once. We can use this thing right here. It is a stainless steel tube and you can insert a wood drill in there. And this way we can slowly add... Andere Richtung. So by connecting this construction to the still, we can spin the screw here and slowly add our reaction mixture to the burning mixture inside the still.
We also bought a larger bucket of water so that the still is almost submerged to the top. We hope to condense the majority of the potassium this way before it can escape the still and ignite. The slow addition of the reaction mixture worked surprisingly well and the reaction proceeded relatively controlled. However, after a while, we noticed that the screw conveyor appeared to be clogged. Apparently, the starting material occupies a much larger volume when added during the reaction, thus causing our still to be clogged up to the top.
Experte Niklas findet das nicht gut.
Oh, gib dir mal die lieben Bohrer.
Wie viele der Mutter sind jetzt eigentlich schon in das kochende Wasser gedroppt?
Eine. Nur eine. Zwei.
After clearing the blockage, we sealed the still and started the distillation. Here you can see me replacing a completely destroyed O-ring. But how did this happen? At the beginning of the distillation, when the still is being heated, the reaction mixture produces a gas that increases the pressure inside the still up to 500 millibars. This gas production suddenly stops at some point and the pressure drops within a few seconds to a few millibars. This brings the pressure below the vapor pressure of potassium at the corresponding temperature. Consequently, a large amount of potassium suddenly condenses in the cooler, transferring the heat from the still to the cooler. This causes the metal and therefore the O-ring to heat up to about 400 degrees Celsius, destroying it. When we noticed this, we quickly introduced argon into the still and turned off the oven to replace the O-ring. We never encountered this problem during small-scale test runs, which highlights the challenges faced when scaling up such a process. The rest of the distillation proceeded relatively uneventful. Our yield was 450 grams, more than the previous week, but still far from satisfactory. Additionally, the potassium was much less pure than before. As you can see, a lot of carbon ended up in our receiving flask. What was not uneventful, however, was opening the still to quench it. A substance had formed that spontaneously ignites in air. Honestly, we have no idea what it is, but it is definitely not potassium. The magnesium we used is likely an alloy containing other metals. However, which one of these could form such a pyrophoric compound is unclear to me. If you have any good ideas, let me know in the comments. On day 3, the weather was not on our side. It rained most of the time, which is not ideal when distilling a highly reactive metal. However, we didn't let that stop us. We suspected that the reason for our low yield was the magnesium. As I mentioned before, it was waste material from milling and turning operations. It was coated with a thin layer of an oil-water emulsion used as a lubricant during milling, and it was also unknown how much magnesium the alloy actually contained. So we bought new, cleaner magnesium. You can see the noticeable difference in color compared to the magnesium on the left side that we used before. Additionally, we ground the magnesium in a mixer to get a finer powder and thus a larger surface area. It was quite impressive to see the temperature of the metal rise to around 80 degrees Celsius due to oxidation in the air. Since we always had problems igniting the reaction mixture, we decided against using single smaller batches to keep the volume down, and again added the reaction mixture continuously. For the future, we plan to ignite the reaction electrically using a resistive heater. Once the reaction was completed, we closed the still and started the distillation. To monitor the temperature of the cooler accurately, we placed 2 temperature sensors on the cooler and the adapter of the round bottom flask. The problem is not only that the cooler can become too hot like it did last time, but it can also become too cold, causing the potassium inside to solidify and clog it. Therefore, we used a heating band to keep the cooler consistently at a temperature above 60 degrees Celsius, the melting point of potassium. Despite closely monitoring the cooler's temperature, we once again encountered the problem of a large amount of potassium suddenly condensing in the cooler and destroying the O-ring. So we replaced the O-ring again and took the opportunity to change the round bottom flask in which we had already collected some potassium. For future runs, I plan on implementing a pressure sensor that automatically opens a valve to the argon cylinder when the pressure suddenly drops. This way we can let the still cool off a little bit at a higher pressure, thus preventing the potassium from boiling over. While we are replacing the round bottom flask, it is a good opportunity to talk about the sponsor of today's video, PCBWay. How am I going to implement a PCBWay sponsorship in a video about making and distilling potassium? Well, you might have noticed that since day 2 we no longer use the homemade and fragile KF25 glass flanges, but instead use a stainless steel adapter piece with a KF25 flange on one side and a female NS29 joint on the other. I simply designed the adapter on the computer, uploaded it to PCBWay, selected the desired material and received an instant price estimate. About a week later, I received the package with the adapters. A huge thank you to PCBWay for sponsoring this video. You will find a link to their website in the video description. And now, back to the distillation. After changing the O-ring, the distillation proceeded beautifully and the flask continued to fill up. It is truly mesmerizing to watch the liquid metal drip into a lake of molten potassium.
Okay, we've stopped the distillation, stopped the vacuum pump and introduced argon into our system. And if you look at our yield, you can see that this 2000 milliliter round bottom flask here is approximately half full, which means it's approximately 1000 milliliters. So we could have a yield of approximately 1 kilogram, and it's not the only potassium we got from this distillation. The first round bottom flask, which we had to remove because our O-ring burned, also contains some potassium. So we will now melt it and see how much we got here.
After the still had cooled down, it was time to quench it again. And upon opening the still, we found something fascinating. Beautiful dendritic magnesium crystals had formed on the wall and especially on the lid.
Alter, Magnesiumkristalle.
Junge, sieht das geil aus.
Either the magnesium evaporates or sublimates directly and then crystallizes on the lid, or it is also possible that a potassium-magnesium alloy forms from which the magnesium crystallizes out when the potassium evaporates. Looking at these crystals, it seems like a very interesting separate project to build an apparatus to specifically grow magnesium or other metal crystals. Let me know in the comments what you think about that idea. To determine the yield, the potassium in the flask was melted again under a layer of mineral oil. Since I wanted a nice ingot of potassium, we then poured the liquid metal into a cake mold. After it had cooled down, we were able to remove and weigh it. "954 grams. Now you might think that we haven't reached our goal here, but we still have the potassium that was collected in the first flask before we replaced it. So let's add that. 1094 grams. You can't imagine how happy I am that we broke the 1 kilogram mark. To get a nicer ingot, we removed the dirty parts of the potassium and melted everything again. While our ingot cooled off, we also melted some of the potassium from our first distillations to make a few potassium muffins. We will use these later in the video for a bit of tomfoolery. And here you see the finished ingot. Unfortunately, the surface was still not perfect, as oil droplets were trapped under the potassium, but good enough to use my 3D printed stamp to emboss the ingot. I overlooked one thing.
Ich habe nicht dran gedacht, dass das gespiegelt ist.
Well. Dann zeig mal schön für die Kamera.
The potassium ingot weighs 1077 grams, which corresponds to a yield of 94%. Considering that the raw materials for this kilogram of potassium cost around $50, this is probably the cheapest potassium made by home chemists. Now that everything else is done, I would say it is time to throw some potassium into water. If you want to see the videos where Elias tests different methods for producing potassium, you should definitely check out his channel. You will also find his version of this project there. The link is in the video description.
Oh, das kann doch nicht wahr sein.
So, what am I planning to do with that much potassium? Well, how about a sodium-potassium rocket engine? I think injecting the liquid and highly reactive alloy of sodium and potassium together with water under high pressure into a combustion chamber and seeing how much thrust we can produce sounds like a fantastic idea. If you enjoy my projects and want to support me financially, I would be very happy if you became a Patreon. You can find the link to my Patreon in the video description. And a huge thank you to my current patrons. You make my projects possible, and I am very grateful to each and every one of you. I would also like to thank Fabian once again. Even though it may have looked like I was doing all the work, he invested many hours over several months into working on the parts, and without him, this project wouldn't have been possible. A big thank you also goes to Markus, who provided us with his workshop and a welder so I could weld the still together. Other than that, thank you a lot for watching.